Mechanics of Material, Chapter 6, Bending, Composite Section, example number 2. So in this example, if we have a composite section consists of two material, a T-section steel part, and two wooden plate attached to each other and handling a positive moment of M. So we do have the dimensions we want to and we do know what the moment is. That's 50 kilonewton meters, and we want to calculate maximum stress in wooden part and also the stress in the top steel part. So and also modulus of elasticity of steel is equal to 200 gigapascal, and wood moment modulus of elasticity is 12.5 gigapascal. So the very first thing we need to do in such problems is to convert the entire section to a unit section. So we need to convert, for example, the steel to wood. In that case, we do have a transformed section which is entirely consist of wood with new dimension. And how to do that is by applying a N, which is the modulus of elasticity of the higher material over the lower material. So ES over EW is 200 over 12.5. And if you do the math, it just gives you a numeric value of 16, which means you have to multiply the horizontal part of a steel by 16 to get the transform section. So like the small part, like 20 times 16 is 32 millimeters, 320 millimeters, and 200 millimeters times 16 is 3200 millimeters, and that's by multiplying the horizontal dimension of the steel portion of the section by a numeric value of 16, we develop a transform section entirely of wood. And the second step in calculation of stress is to calculate the centroid from a base. So if we just consider our base like at the very bottom of the section, y bar is equal to summation of a area times in a midpoint of that section or centroid of that section over the summation of the area. So if we just consider our base from here, and this is our y bar calculation, and if you do so, we do have two part, like the top part, which is 3200 millimeters times 20 times a half of this part. This is 300 up all over to here plus 10, which is halfway through the centroid of this top part, and times second area 470 times height times centroid, which is 150 from the very bottom over the summation of area. It gives you almost 200 millimeters in terms of y bar, location of neutral axis or line. So the second part in calculation of stress is moment of inertia calculation. Again, we do have two part, like total moment of inertia is I1 plus I2, and each of them consists of a 112 base cube height plus AD squared, because there is a distance to the centroid for those sections. So if we do the mass for I, it just says 112 base cube height for this part, 112 base cube height, and this is the height plus AD squared. And then we do have AD, which is the area, times D squared, which is the distance if our centroid location is at 200. So it just says this is a 200 y bar. We already calculate y bar to be 200 millimeters. So, and the centroid of this section, like A1, y bar 1 is equal to 150. So there is a distance, we call that d. D is equal to 50 millimeters. We just have replaced this number, numeric value, over here, which is our a d squared part for the first part. Do the same for the second part, and it just gives you this centroid now is located like this distance. So D2 is 110 millimeters. And then it just gives you overall moment of inertia 2.19 times 10 negative 3 meter cube, meter to the force. And so if you want to calculate the stress due to a bending, if you remember, sigma is mc over I, and like C1 for the very bottom part of wood, that's the farthest distance for the wood part, and this is like for the top steel. So if you want to first calculate the maximum stress in wood, just go all the way down to the farthest distance of wood from the centroid of the entire section, and we call that C1 like 200 millimeters or zero point 0.2 meters. And then replacing the numeric value, moment is provided, distance is provided, I is from here, M is already provided in problem statement, 50 kilonewton meter. And if you do the math, it just gives you sigma in wood. Maximum stress in wood is 4.57 megapascal. And like in a stress in top steel, because if you remember, we have also a steel like at the bottom, but we don't consider this a steel right now. Our problem statement just talk about the steel at the top, so we just go with this part, so we need to consider C2. So just remember, in a steel you have to multiply your stress by N, because a steel has a E which is 16 times E wood. We already calculate N, which is ES over EW. If you remember, that was 16, so we need to use this 16 over here. If you do so, it just gives you a numeric value of 43.83 megapascal, almost 43.8 megapascal. If you want to show it in the graphically in the figure, it just certainly says sigma in wood is much less than a stress in a steel due to higher modulus of elasticity, much higher modulus of elasticity. Thank you. We'll solve more problems in uh, combined or uh, multiple section calculation problems.